All right, welcome to physics lesson 5.04. We are introducing friction on this video. And so what we're really going to kind of be doing is talking about it in more of a qualitative sense rather than a quantitative. We will do a sample problem. So if I have a box, if I have a surface, and I have a box on that surface, and I'm dragging that box along the surface, we all know there's going to be friction. If I could take a small piece of this and blow it up, what I would see is that even like if it was linoleum and it was a cardboard box, the surface of the linoleum is going to have microscopic jags, and the surface of the cardboard is going to have the same. And no surface is perfectly smooth. And so what's going to happen is as I'm pulling this, let's say my motion is this way, the nooks and the crannies in the floor are going to pull and resist the motion for the box. So the first thing we're going to say about friction is it always acts in the opposite direction of motion, or is always acts counter to motion. It always acts counter to motion. We have, so these are all points for friction. We have categories of friction. One that we're not going to deal here until later is rolling friction. We have sliding friction. And we have static friction. The static is the friction that you run into when you're trying to start something moving. So this is sliding is what it sounds. Static is when the object is not moving. And we're trying to start motion. Trying to start motion. So if you've ever tried to push something heavy that doesn't want to get going, if it's on a surface, it's tough to move. You know that once you get it going, it's easier to keep it going. So we usually talk about sliding friction as being less than static. And if we're talking about sliding friction, let's start with sliding. We call that kinetic. So sliding friction, we can call that kinetic. Our symbol is, let's wait, I want to talk about something else first. Yep, I'm gonna shift gears here. So we talk about friction. Just table this for now. We'll come back to that. Friction is related to the normal force. So remember that the normal force is the force that's exerted on an object by a surface. So in this case, the normal force is being exerted on the box by the floor at a 90-degree angle. Well, it kind of makes sense, doesn't it? Because we're talking about already a force that exists between the floor and the box. Friction is tied to that. So in a sense, you can think of it as being like if it's a dry linoleum in a cardboard box, maybe it's 80% of the normal force. What's going to happen is if we get this wet, you're going to have a smoother surface in a sense. Now I'm oversimplifying that greatly. And so maybe it would drop to about 40% of the normal force. that correlation, that relationship between the two, we call the coefficient of friction. And I like to think of it as a percent because it's unitless. So first of all, it's unitless. We use the symbol is the Greek letter mu. And for static friction, this is going to be mu sub s. And for sliding or kinetic friction, that's going to be mu sub k. So those are the coefficients. What else did I want to say about these? Smaller mu translates to lower friction force. So let's look at some of these values. Let me do surfaces. I'm going to make a little table here. So we're going to go surface. We're going to go mu sub s and mu sub k. So let's say I'm sliding a wood block across a wood block, so wood on wood. There is a coefficient of static friction of 0.4 and kinetic friction 0.2. Well, why the difference here? Remember, it's easier to keep something moving than it is to start something moving. So this is static, so we're trying to get it moving versus we've already gotten it moving. Let's take rubber on concrete. That's got a static coefficient of static friction of 1 and a kinetic is 0.8. I think the one that amazes me is I forget what ice on ice is. It's like point 0.1 and 0.08. But if you look at your joints, the synovial fluid in your joints, our joints do a better job at reducing friction than even ice on top of ice. So that's kind of nuts. Well, how does this work? If friction is related to the normal force and the coefficient of friction, you can think of this as like almost like a percent of the normal force. That's the way I like to think of it. The way we would write friction for sliding friction. So if we're looking at sliding friction here would be mu sub k times Fn. So let's do a quick sample problem. If I'm sliding a 1, or we would say a 1 kilogram block is sliding across a wood floor, Floor, what is the force of friction? All right, well, let's start off with the free body diagram. Okay, the first thing you're going to have to ask yourself is, what are my forces? Well, I've got my weight vector. My motion is here. So that means my vertical forces have to be equal and opposite because I don't have vertical motion. Now, it doesn't say I'm pushing a block across the floor. It says a 1 kilogram block is sliding across the wood floor. So I've got friction that's acting in reverse. So I've got my weight vector, I've got my normal force, and I have the force of friction. Okay, so I know that the force of friction is mu sub k times F sub n, And if I look at my table, wood on wood is going to be 0.4. Well, do I have F sub n? No, but I know F sub w. F sub w is going to be 1 times 9.81 negative, let's assume a coordinate system. That means this is going to have to be positive 9.81. Oops. So if I take 0.4 times 9.81, that gives me my friction force. And again, think of it, it's like 40%. Did I use the right? Ugh, I used the wrong coefficient. I grabbed mu sub s, it should have been mu sub k. So in the sense, I'm looking at like 20% of my normal force. So 9.81 times 0.2 is going to be 1.96 newtons. Now, if I had said I'm pushing a kilogram block, or I'm pushing a block across the floor, then I'd have an applied force, and that would be a little bit of a different problem. Well, what you saw me do there, I'm going to take my mistake and I'm going to use it as part of the lesson, is I grabbed the wrong coefficient. So that was, I grabbed the static friction, and I needed the kinetic. So let's talk just a little bit about this static friction before we move on. So the formula for static friction is similar. So I've got my force of friction static, and I should probably add a kinetic up here, is equal to the coefficient, hold on, less than or equal to the coefficient of static friction times the normal force. And this is what we need to talk about. What's up with this less than or equal to? So if I look at the force, so if I talk about, or I consider the force I need to start motion, I'm talking about F FRS equals mu sub s Fn. At the point where my motion just starts, these guys are equal. But let's say I find out that it takes an applied force for this to be equal. Okay, so let's take a scenario. I'm gonna have to kind of work my way up here. So if I have a block on a surface, and I've got friction, and I've got an applied force, and I've got a normal force, and I've got weight vector Fn, Fw, Fa, FFR. These all, I try to make these all equal. So I'm not moving. If this is the point where motion starts, everything, the applied force and friction force, everything would be equal. But let's say this applied force at the time the motion starts is 20 newtons. Well, what if I push on this block with 5 newtons? Does that mean that, and then this is going to be negative 20 newtons. If it takes 20 newtons to get this moving, what happens if I push on this block with 5? Well, I'm going to have 5 newtons this way, and I'm going to have negative 5 newtons this way. Am I going to have the same friction force? No. So this is when motion starts. But this less than, I can have friction force that's less than the motion I need to get started. So this could be negative 1 Newton. It could be negative, 5 newtons. It could be negative 8 newtons. And that means that this isn't necessarily, this is the value. So these values are max values. You can have a coefficient of static friction that's less than this, but that's the max. Because when we talk about these, we're talking about when motion gets started, but your coefficient for static can be a little bit different. So these are max. These are pretty consistent because once I'm sliding, then it usually doesn't change unless my material changes. But one of the takeaways, friction depends on the material. Let me keep my color consistent. Let me go with red. So takeaway number 4. Friction depends on the 2 material types. It depends on the 2 types of material. So let's sum up. Friction always moves counter to motion. So my motion's this way, my friction's got to be this way. There are categories of friction. We're going to talk about sliding friction and static friction. Friction is related to the normal force, and we think of the coefficient of friction as being some kind of a percent of the normal force. So for kinetic, that's kind of fixed. For static, these give us our maximum values, but they could be lower. And then finally, friction depends on the type of materials. I would say 5th are our formulas. So we've got, and let me rewrite. Got friction for static and friction, is that going to fit? Nope. Kinetic equals mu sub k F sub n. So we have equations. All right, we're going to get into how to use these equations and how to apply this information in the next 2 videos. Thanks for watching.